In this last part of Lecture 4, we will examine the titration of a weak base by a strong acid. And then at the very end of this part, we'll do a quick overview comparing the 4 different types of titration curves that we've covered. If you remember from Lecture 3, actually example 4 from Lecture 3, we looked at the titration of 20 milliliters of 0.1107 molar ammonia, the weak base, by the strong acid, 0.1 HCl, and the HCl had a concentration of 0.1400 molar. From that example, we learned that it took 15.81 milliliters of the HCl to reach the equivalence point. The pH at that equivalence point was less than 7. More precisely, it was calculated to be 5.23. And as with previous examples, if we monitored the pH as we added small amounts of HCl titrant, and we went not just to the equivalence point, but beyond the equivalence point, the titration curve would look like this. And you can see we've marked the equivalence point at 15.81 milliliters of added HCl. So as we've done before, we'll look at the pH or calculate the pH at 4 different spots in this titration. So we'll examine the pH at 4 different places before we add any titrant to the flask, at a spot that's between the initial pH and the equivalence point, at the equivalence point, of course, and then a point beyond the equivalence point where we've added excess titrant. As usual, we need to count the number of formula units of what's in the flask. In this case, it's ammonia in that 20 milliliter solution. That's easy. You just take the concentration of the ammonia in the flask times its volume. We get 2.214 times 10 to the minus 3 moles of ammonia. Of course, what we're interested in is what the pH is there. At this point, certainly the hydroxide ion concentration is not 2.214 times 10 to the minus 3 moles because this is a weak base. So we need an ice table. What we're doing is essentially calculating the pH of a 0.1107 molar solution of the weak base ammonia. If we set up our ice table using the usual methods, we get a hydroxide ion concentration of around 1.4 times 10 to the minus 3 molar and a pH of 11.15. Again, this is our starting pH in the flask before any titrant is added. Now this initial pH is much lower than the pH we saw when we titrated the strong base, KOH, by 0.1400 molar nitric acid. And that makes sense because in this case, we have a weaker base in the flask, so the pH should be lower. Well, how about the pH between the initial and the equivalence point? We're going to calculate the pH after we've added 7.14 milliliters of HCl titrant. We can calculate the number of moles of HCl we've added, which would be equal to the number of moles of hydronium ion added by taking the volume added times the concentration. We get here the number of moles of hydronium ion that we've added. That hydronium ion will react with ammonia to produce ammonium ion. So before any addition of the titrant, we had 0.002214 moles of ammonia in the flask. When we add our 0.0009996 moles of hydronium ion, we will react with the ammonia, so we destroy that many moles of ammonia and produce that many moles of ammonium ion. So what's left? Well, after the reaction with the hydronium ion, we have 0.0012144 moles of ammonia left in that flask, and we've produced this many moles of ammonium ion. Well, we have a situation where we have significant amounts of both a weak base and its conjugate acid, so we have a buffer. If we roll out the Henderson-Hasselbalch equation, the pH would be the pKa of the acid form of this equilibrium, the pKa of the ammonium ion, plus the log of the ratio of the moles of the base form over moles of the acid form, and we get a pH of 9.33. You notice in the table here, the pH says 9.34. There's a subtle difference in the two values we get here and here. In the table, this was calculated from Excel. There's just some subtle differences in rounding. How about the pH at the equivalence point? Well, if you recall, in lecture 3, when we did this example, we said the pH at the equivalence point needed to be less than 7 because one of the products is acidic in water. That would be the ammonium ion. We actually did take the time to explicitly calculate what the pH would be when we had 2.214 times 10 to the minus 3 moles of ammonium ion in a total volume of 35.81. That would be the total volume at the equivalence point. And we said it would be 5.23. Now, without doing a calculation, we could use our titration curve to get that information. If we estimate the equivalence point, as before, as being halfway up this, well, in this case, halfway down the steep descent, we can get an equivalence point volume at that point by reading it off the x-axis, and then we would get the equivalence point pH by reading the pH off the y-axis. In any event, clearly the pH at the equivalence point is less than 7. Well, how about the pH when we add excess titrant? Well, after the equivalence point, we have reacted all of the initially present weak base ammonia. We've produced ammonium ion, but as we continue to add titrant, that strong acid titrant pretty much takes over the pH and totally dominates the solution. So the pH would pretty much just be determined by the number of moles of excess HCl that we add divided by the total volume. Now at this point in the titration, the number of moles of hydronium ion added, or HCl added, would be 23.43 milliliters. That would be the volume of titrant added at this point times its concentration, to give 0.0032802 moles of hydronium ion. So the excess number of moles of hydronium ion that we're dealing with would be the total number added minus the number needed to reach the equivalence point. So this here would be the excess number of moles of hydronium ion in the flask at this point. If we take that and divide by the total volume in the flask, we get a hydronium ion concentration of 0.02455 and a pH of 1.61. Well, how about picking out an indicator? Well, If you recall from lecture 3, we actually projected that methyl red, bromethymol blue, or methyl orange would all or could all be suitable indicators. Interestingly here, unlike the previous titrations, phenolphthalein does not appear to be suitable here. So let's demonstrate why phenolphthalein is not great here. What we say is that it produces an unacceptably large titration error. If we take a point about in the middle of that phenolphthalein color change and we find the volume of titrant added at that point, we get 14.74 milliliters. So what we call that is our endpoint volume for phenolphthalein. The equivalence point volume, that would be the volume at the equivalence point, is 15.81. So our titration error there is a little over a milliliter. That's an intolerably large titration error, and the other indicators would give a much lower titration error. So in this case, phenolphthalein would not be a suitable indicator. Let's look at the strong base titrated by a strong acid, the example we covered in part 3, with the weak base titrated by a strong acid. That's the one we're doing now. What I did here was I stretched the y-axis to reach a pH of 14 for our weak base so that we could compare these two a little more directly. These are identical titrations in the sense that each flask starts with the same number of moles of base in a 20 milliliter volume, same concentration of base. In the one case, of course, we have a strong base and the other a weak base. And in both cases, the titrant is 0.1400 molar of a strong acid. In the case of the strong base, strong acid titration, it was nitric acid. In the case of our weak base titrated by strong acid, it's HCl, but both are delivering hydronium ions in the same way. So what's similar about these two? Well, both titrations require the same volume of titrant to reach the equivalence point. Both titrations show a pH of 1.61 when we've added 23.43 milliliters of strong acid. That would be about 7.6 milliliters beyond the equivalence point. They both show the same pH because remember, the pH beyond the equivalence point is totally dominated just by the number of moles of excess titrant that we've added. So what are some differences? The initial pH value and the rest of the pH values before the equivalence point are higher for the strong base. That makes sense. The weak base titration shows a somewhat rapid initial decrease, but then that change levels off in what we call the buffer region. The pH values at the equivalence point are different. That's, of course, been explained several times previously. The biggest difference that most cite is that the rapid drop in pH for the strong base titrated by strong acid is much larger than the rapid drop for the weak base titrated by a strong acid. And for the weak base, that rapid drop can become less and less if the base is very weak, in other words, has a small Kb value and is or very dilute. So for very, very weak bases, the equivalence point, this drop would be much, much less, and it would be harder and harder to pin down an equivalence point. For ammonia, it works fine. There is one additional piece of information that we can get from the titration curve of the weak base titrated by a strong acid, and that is the Kb of the weak base. So let's look at how we would do that. The pKb of the weak base can be extracted from the pH at the half equivalence point on the titration curve. So the equivalence point volume is 15.81. If we divide that by 2, we get 7.905. And if we look at the pH at this half equivalence point, halfway to the equivalence point on the x-axis, we get 9.26. You have to be cautious here. This is not the pKb of ammonia, but rather it's the pKa of its conjugate acid. So let's go back to the Henderson-Hasselbalch equation. At the half equivalence point, the number of moles of base form exactly equals the number of moles of acid form because we've titrated exactly half of the ammonia. And that makes the second term of the Henderson-Hasselbalch go to 0. And let's demonstrate this. At that half equivalence point, the number of moles of hydronium ion added would be 0.001107 moles. Here's the reaction that's going on in the flask. Before we add any hydronium ion, remember we had 0.002214 moles of ammonia, not much ammonium ion. We're going to destroy 0.001107 moles of ammonia with the hydronium ion and produce that same number of moles of ammonium ion. So at this half equivalence point, after we've added the 7.905 moles or milliliters of titrant, we have exactly the same number of moles of the base form as the acid form. Now the pH at this point is 9.26, and we say it's equal to the pKa plus the number of moles of ammonia over ammonium ion. That log term cancels out because we'd have log of 1 or 0. So the pH, which we know is 9.26, is simply equal to the pKa, and it's the pKa of the ammonium ion, 9.26. Looks like I have a comma here, should be a decimal point. So now what do we do? Now recall from Module 5 that for conjugate acid-base pairs, the pKa of the acid form plus the pKb of the base form equals pKw, or 14. This looks pretty straightforward. This means the pKa of the ammonium ion plus the pKb of ammonia, the base form, equals 14. We know the pKa of the ammonium ion is 9.26, so the pKb of ammonia is 4.74. Therefore, its Kb is 1.8 times 10 to the minus 5. So we've been able to measure the Kb of the weak base from the data obtained from the titration curve. Remember, and we've mentioned this in earlier lectures, 1.8 times 10 to the minus 5 is also the Ka of acetic acid. And again, does this mean anything? No. The fact that they're the same is purely coincidence. So let's conclude Lecture 4 with a general overview or comparison of the 4 different types of titration curves that we covered. We looked at a strong acid being titrated by a strong base, followed by the titration of a weak acid titrated by a strong base. The third example was a strong base titrated by a strong acid. In the example we just covered in this last part, a weak base titrated by a strong acid. Now, despite some differences in the actual acids and bases and in the concentrations used, we can still make some general comparisons between these different types of titration curves. One of the first things we noticed was that when we react a strong acid with a strong base, whether the pH is rapidly increasing near the equivalence point for this titration or rapidly decreasing near the equivalence point for this titration, we found that the change in pH near the equivalence point was quite large, as opposed to a much smaller change in pH near the equivalence point when we have a weak acid or a weak base in that flask. Of course, we drilled into you that the pH should be equal to 7 at the equivalence point when the reaction involves a strong acid and a strong base. When we have a weak acid in the flask being titrated by a strong base, the pH should be greater than 7 at the equivalence point. When we have a weak base in that flask titrated by a strong acid, the pH should be less than 7 at the equivalence point. And finally, we can get the pKa of the weak acid at the half equivalence point. So for a weak acid titrated by a strong base, the pH equals the pKa of the weak acid at that half equivalence point. When we're titrating a weak base by a strong acid, we don't get the pKb directly of that weak base at the half equivalence point. The pH at that half equivalence point equals the pKa of the acid form of the weak base, from which we can calculate the pKb of that weak base.